Welcome to Maths for All. I'm Aisling Flynn. This is higher level. Today we're doing limits and sums to infinity of geometric sequences. So what are limits? Consider this pattern: 3, 6, 12, 24, 48. Clearly the numbers are getting bigger and bigger by a ratio of 2 each time. Okay? Is there a limit or stopping point to how big the numbers in this pattern get? No, there's not. It will finish at infinity, which is to not finish at all, to go on forever and ever. This sequence is said to be divergent, or getting broader and broader. Its range is getting bigger and bigger. If we were to graph it, this line was 0, then it would start slowly and it would get broader and broader and broader and broader. So to get wider means to diverge. So this is called divergent. And just to take a note of our R value there, R in this case was 2, so R is greater than 1 is a test, or the absolute value that R is greater than 1. It could be negative and it might diverge this way. Okay. The absolute value greater than 1 is a test to see is your sequence divergent. Okay, consider this sequence: 1, a half, a third, a quarter. Okay, so we can see that the denominators are getting bigger, but actually the value of the fractions is getting smaller. Okay, so if we look at the value of the fractions, that's we have 1, 0.5, 0.3 recurring, 0.25, so on. 1 over 1,000 is 0.001. Okay, because the numbers we are dividing by is getting bigger and bigger, the value of the fraction is getting smaller and smaller, and 1 divided by infinity is infinitely small, so a teeny tiny number, but it never quite gets to 0. Okay, that's the key part. Is there a limit to how small the numbers in this pattern get? Well, they get smaller and smaller and smaller. We say they are approaching 0, so they get very, very, very close to 0, but they don't quite reach 0. And this is what's known as a limit. We say the limit is 0. And this sequence is converging. So converging means to get closer and closer. It's converging towards 0. Okay, if we were to graph that particular sequence from the number 1, it would fall rapidly and then even off. It gets closer and closer and closer and closer to 0, but never quite reaches 0. It's converging. Okay, and the R value, you see this in a minute, is less than 1. The numbers from term to term are getting smaller. Okay, that's not quite a geometric sequence above, so it doesn't have a constant R. Okay, a sequence is converging when the absolute value of R is less than 1, or you can say that R is between -1 and 1. So that's a test for converging sequences. You'll need this later. Okay, limits. So there's our sequence. It is in the form of 1 over n. So if you look there, that the first term, t1, is 1 over 1, which is 1, t2 is 1 over 2, t3 is 1 over 3, and so on. So this is our tn formula, if you like. Okay, and we can describe the limit as n goes to infinity of our sequence 1 over n equals 0. So we discussed on the previous slide that the limit is 0, and we read it as the limit as n goes to infinity. So as n gets bigger and bigger and bigger of this sequence, which has the shape 1 over n, equals 0. So the fractions, the terms, as n gets bigger and bigger and bigger, the overall value of them gets smaller and smaller and smaller, going towards 0. So similarly, 1 over n squared, as n gets bigger and bigger and bigger, the overall fraction gets closer and closer to 0. So the limit of 1 over n squared as n goes to infinity is 0. And in actual fact, that's true for any power of n, provided the power is positive. Consider this one. 2 times infinity over 3 times infinity. Well, infinity divided by infinity is 1, so we get 2 over 3. Okay, so the limit of something like 2n over 3n, okay, you can see as n goes to infinity, so this would become ridiculously large and this would be the same, but we know that n divided by n is 1, so we get 2 over 3. And let's look at one where we have different powers of n on different levels. One of these n's would divide into one of the n's under the line, and we get the limit as n goes to infinity of 2 over 3n. And on the previous page we saw that anything with an n as a denominator, as that goes to infinity, the limit of the overall fractions are 0. Okay. So consider what happens to different powers. Let's take this example. So quadratic divided by quadratic. We're going to see what happens with different values of n. So I want you to pause this now, use your calculator and evaluate the fraction when n is equal to 100. Okay, and I think you'll find you get these answers. So 0.7238 when n is equal to 100, 0.6951 when it's 200, and 0.6723 when it's 1,000. Okay, so they're all quite similar in around the same area. They're getting smaller, but they're slowing down getting smaller. So I believe they're approaching some number, okay, smaller than 0.6723 when n gets to infinity. Okay. Note that the n squared terms are far more significant than n and the constant terms as n goes to infinity. So as n gets bigger and bigger and bigger, the n squared parts are the biggest amount of the fraction and the other parts are not so important. Okay, so we're going to say that the limit of this fraction as n gets bigger and bigger and bigger will be as if you had 2n squared over 3n squared. The rest of them don't matter so much, okay? And so what you appear to get then is 2 over 3, and that's the limit of this fraction. As you use bigger and bigger values of n, it gets closer and closer to 2 over 3, which is of course 0.6666, so the number 6 recurring. Okay. So the method by which to find limits is this. Divide all terms by the highest power of n. Any terms with n or n squared as a denominator have a limit of 0, as we already discussed, and any constants will remain. So applying the method here, we would divide every single term by n squared, which was the highest power of n in the original fraction. Okay, what we get then is 2 plus 15 over n minus 1 over n squared on the top, and 3 minus 3 over n plus 2 over n squared on the bottom, and anything with n or n squared as a denominator will have a limit of 0 as n goes to infinity. And so we get the answer. The limit for the whole thing is 2 over 3. Okay, so this is a practice one. You can try that yourselves, pause the video, go through the process. But if you examine here, the highest powers are x squared. And I think when you go through the process, you should get the answer 4 over 3. But I would like you to try that yourself. Okay? Now, properties of limits. These are available in your formula and tables books. When do you use these? Well, when you're asked to evaluate a limit and you have something plus something, you can get the limits of those somethings, those functions separately, and just add them at the end to give the overall limit. Same for subtraction, multiplication, division. The limit of a constant is just itself, okay? It's not going anywhere. And the power, you can find the limit of the function, and when you get that limit, then apply the power to it, okay? Now, what about this one? Evaluate the limit of this. Now, the method is to divide by the highest power of n. Right, I see an n squared, but it is under a square root sign, and the square root of n squared is just n, isn't it? So, what do we do here? Well, I would like to compare like with like, top and bottom. Okay, so this is what I'm going to do. Okay, I'm going to leave for a moment the square root of 4n squared plus 5 there. Now I'm going to square the denominator, but also square root it. So mathematically I'm not changing it. I'm doing that so I can include it under a square root sign so I can compare like with like, top and bottom. Okay, so I get the square root of 4n squared plus 5 is on the top, and square root of n squared plus 2n plus 1 is on the bottom. Or I could write that as included all under the 1 square root sign, 4n squared plus 5 over n squared plus 2n plus 1. Okay, and now I can compare like with like. Now we can use n squared as the highest power, okay, while keeping that square root sign. So we'll have 4n squared over n squared plus 5 over n squared all over n squared over n squared plus 2n over n squared plus 1 over n squared. Okay, so continuing over here to the right, just tidy up a little bit. Okay, my square root sign, I will get 4 plus 5 over n squared. Okay, and underneath I'll get 1 plus 2 over n plus 1 over n squared. So now applying the limit, what we know about limits, we will get our limit equal to 4 plus 0. So anything with an n or n squared underneath it, its limit is 0. Okay, so essentially we arrive at square root of 4. So the answer is 2. Okay, so that's the limit of that. Now, the sum of infinite series. So we've been talking about infinity when n goes to infinity. Consider an infinite geometric series where a is 1 and r is 1/4, such that each term is given by. So that's our regular form. The series begins. So I'd always start out by writing out the first few terms. So 1 is a, and multiply that by 1/4, we get 1/4. And each time we're multiplying by an extra quarter, so we get different powers of 1/4. If you wanted to evaluate, that first one would be equivalent to 1, or the third term would be 1 over 16, the fourth would be 1 over 64, the next one would be 1 over 2, 5, 6, and so on. Okay, so the numbers are getting smaller and smaller. Our r is equal to 1/4, which is less than 1. So we do have a converging sequence. Okay. So the first few partial sums are, so if we add some of them, a few of them, so S1 is just 1, S2 is 1 plus 1/4, S3 is the first 3 terms, so 1/4 squared was the third term, and so on. Now, let's evaluate them. You can use your calculator there, and we get decimal values just to look. So the first one is 1, S2 is 1.25, S3 is 1.31, so you can see that the growth is slowing down because each time you're adding on a smaller and smaller amount. and S4 is 1.328. Okay, remember that in your head, 1.328. All right, so the growth is slowing down. Okay, the series was a converging series. So yes, I do think we'll have a limit. It's approaching some value, but we'll never quite reach. Now, sum of an infinite series. What about S20? We're going to use the Sn formula for geometric series. There we have it. Sub in 1 for A, quarter for R, and 20 for N. There we go. My calculator says 1.3333. It doesn't use 1.3 recurring, okay, which implies to me that somewhere down the road here there might be some other numbers, okay. Sum of infinite series. So it's clear that the series is converging. Each additional term is getting closer to 0. It follows that with each additional term, the sum is getting closer to some limit. To get the sum to infinity of a series, we use the Sn formula and we get its limit as n goes to infinity. We call this S infinity. So we're going to take Sn and find the limit as n gets bigger and bigger as it goes to infinity. So we substitute our Sn formula in there. We look at what happens to the numbers as n gets really large. Now, the only place that n appears is as a power of r. Now, our series was converging, which meant that r was less than 1, or in the previous example, r was 1 over 4. Okay, and as we got bigger and bigger powers of that, this got to be a smaller and smaller value. So its limit is 0. So that's the only thing that changes on the next line. So we can simplify and say that S infinity equals A over 1 minus R. And that formula appears in your formula and tables book, and you can use it when you need to. Now, just an explanation of other notation you come across, and this is sigma notation. Okay, sigma means sum, so to add up. Okay, so you're going to be adding things. N equals 0, so that's under the sigma sign. That tells you when to start, or what value of n to start with. So note that it sometimes starts at 0 and it sometimes starts at 1. Okay, and the infinity at the top of the sigma sign, this is the final value for n. And note, for partial sums, this is given as a numerical value. Okay, so what we've been shown above translates to. So you start with your formula here. So they can give you many different kinds. They tell you begin with n equals 0. So when n equals 0, anything to the power of 0 is 1. So that gives you for the first term just a. And then when n is 1, you have a r to the power of 1, a r to the power of 2, a r to the power of 3, so on and so on. And the sigma part tells you to put a plus between them all, to add them all. Okay. If you wanted to write a regular sum with it, let's say you had some term where Tn was equal to 2n plus 1, then your sum, or your S5, you could write it as the sum from when n equals 1 to 5, so start at 1, finish at 5, of 2n plus 1. So what you do is you put your n in each time. So we're starting at 1 this time. 2 1s are 2, plus 1 is 3. Second one, when n is 2, you get 2 2s are 4, plus 1 is 5. Now notice I'm putting a plus between each part because it is a sum. 3s give you 7, 4s give you 9, and 5 gives you 11. Okay, so this is my sum. And if you add those up, we get 25. So my S5, or this sigma, gives me 25. Okay. Now partial sums, this is to repeat that, can be written using the sigma notation also, taking the geometric series with general term. So let's say our Tn was 2 by 3 to the power of n. to write the sum for the first 20 or to write S20, that's what you would write. So you're starting at n equals 1, you're finishing at 20, and sigma means sum. Okay, here's an example. Evaluate the following. Okay, so we're starting with n equals 1 and finishing at infinity. So this one is a sum to infinity. Now, firstly, to answer, okay, I already know I'm going to use my S infinity formula, okay, to get my sum to infinity. But to first identify what A and what R are, I'm going to write out a few terms. So substitute in the starting value of n, which is 1. All right, so 1 minus 1, of course, will give me 0. You see that on the next line. 2 minus 1 is 1, and 3 minus 1 is 2. Okay, so you substitute in for your n's. Just give you a quick look at it. Evaluate, so at power of 0, anything to the power of 0 gives 1. So we get 1, 1/3, 1/3 squared, and so on. So from this, we'll see that A is 1 and R is 1/3. Okay, and now we'll revert to our S infinity, okay, formula. We'll forget about sigma, and we have a value for A, which is 1. We have R, which is 1/3. So under the line you have 1, take 1/3 is 2/3. When you divide by a fraction, you multiply by it upside down, and we get 3/2. Okay, so 3/2 or 1/2 is the answer, the sum to infinity. Now here's an example. The sum to infinity of a geometric progression is 16, and the sum of the first 4 terms is 15. Find the first 4 terms, and there are 2 possible series. Okay, so we don't have a lot to go on. We do have sum to infinity, that's S infinity. We know it's geometric, so we're talking A's and R's, and is 16 equals 16. And we're told the sum of the first 4 terms, S4, equals 15. Okay, so how can we use this information to solve? So I think we first have to identify what A and R are to be able to find 4 terms. So let's use what we have. We have sum to infinity, which is A over 1 minus R. Okay, we don't know much, but we do know that the answer is 16. And we also have S4, which is A by 1 minus R to the power of n. So that's 4 over 1 minus R. And we do know that that is 15. Okay, so how to use these two together? We have 2 equations, 2 unknowns. So it is a form of simultaneous equations. We can't do elimination. We could do substitution, but I'm going to do equating. Okay, so to equate means to put 2 things that are the same equal to each other. I see this letter A as easy to isolate in my equation. Okay, so A equals 16 by 1 minus R from that one, and A equals now 15 by 1 minus R, so multiplying by the denominator there, but also let's divide both sides by that bracket. Okay, so now I've got 2 A equals, so let's equate, put them equal to each other. Sorry, now 1 minus R equals 15 by 1 minus R over 1 minus R, or 4. Okay, now to make life a little easier, I see 1 minus R on both sides. I'm going to divide by that, both sides, and that disappears. And don't like fractions, let's multiply both sides by 16 by 1 minus R, or 4. And we're solving for R, so let's isolate it. Divide both sides by 16. Okay, and to get R by itself, we bring that 1 over. So I get minus R to the power of 4 is equal to, now 1 difference there is 1/16. Now I have negatives. I multiply both sides by positive or -1, make them positive. Now, okay, we're not in too bad a place. Lots of work to do here. Okay, moving to my right. So the power of 4, okay? And I want to solve, I could get the 4th root, or if you spot it, 16 is 2 to the power of 4, isn't it? Okay, or I could have, so really I could say that by comparison, r is equal to half. Okay, right, that's grand. Have r, I can find a. However, read back here, there are 2 possible series. How does that arrive? Okay, and it comes from this. We have an even power. So r to the power of 4 could end up being plus 1 over 16 if r was minus a half also. Okay, so when you have even powers, you have the possibility that the root is plus or the root is minus. Okay, so that gives me the 2 possible series. Now, what do we have to do next? We have to return and we have to solve for a. So I'm going to do use that. Oops, what's going on there? Okay, a equals 16 by 1 minus r. So 1 minus a half. Okay, so 16 by 1 take a half is a half. So I get a is 8. Or I get a is equal to 16. 1 minus a half is 1 plus a half. So that's equal to 16 by 3 over 2. So that's 48 divided by 2. So a is 24. So we have 2 different values of a, 2 different values of r. The question asks you to write the first 4 terms. So if we use the 8, we start with the first one, 8, and r was a half for that. So multiplying by half, we're getting half of 8 is 4, half of that is 2, half of that is 1. And so that's our series. Or, okay, so technically there we had 8, 4, 2, 1 for the first one, where r was plus a half. The second one had r equals minus a half, started with 24. Now half of 24 is 12, but using minus a half you get minus 12. Half of that is 6, and we have plus 6 for the second one, and half of that is minus 3, using r as minus a half. So every second one is negative. Now to check, are we right? In the first instance, we're told that the sum of the first 4 terms was 15. Okay, so let's check. 8 plus 4 is 12. 12 plus 2 is 14, and that is 1 is 15. Correct. Now if we look at this one, in positive numbers we have plus 30. In the negative numbers we have minus 15. So 30 take 15 is also 15. So correct. Okay, so last example, these ones come up a bit. Write the recurring decimal 0.636363 means it keeps going as an infinite geometric series and hence as a fraction. So infinite geometric. So whenever this word infinite is used, I want you to start thinking S infinity. Okay, but where is our pattern and how do we get A and R? Okay, so we have to start with this number and we're going to split it up into different parts. This part, this part. So you break up the recurring pattern. So 0.63, that first part, it's 63 hundredths. Okay, and plus 0.00, so they're gone 63 plus 0.000063. Okay, so what are we adding? We're adding 63 hundredths, so changing them to a fraction, plus 63 thousandths. Okay, so we're jumping in groups of 2, okay, 2 decimal places. Count the decimal places and that's how many digits you should have in the denominators, or how many zeros. Actually, that should be 10 thousandths. So match the decimal numbers to the number of zeros. Okay, 1, 2, 3, 4, 5, 6. So 63 over 1. 1, 2, 3, 4, 5, 6, and so on. Okay, so now we can identify from our pattern that A is 63 over 100 and that R, so the 63 is staying the same, so nothing changing on top when we multiply, but we are multiplying by 100 each time. We're adding 2 extra zeros each time. Okay, so then we simply use our S infinity formula. Okay, let's put 63 over 100 on the top line, 1 minus R, 100 on the bottom line. We have 63 hundredths divided by 99 hundredths. Now we know that to divide by a fraction, you multiply by it upside down, and the hundredths will divide into each other, give 1. We get 63 over 99. Okay, and that is the fraction that is equivalent to this recurring decimal. Okay, we've used geometric series to show that. Find the range of values of x for which the following series converges. So keyword here is converges, and we know that the absolute value of r should be less than 1. So it should be a smaller value than 1 if it is to converge. Okay, so first thing is to find r, and that is to take second term divided by the first term, or third term divided by the second term. So, oops. Okay, so no x there. All right, so 4 divided by 2. So it is 2x. You can see that straight away from just the first two. All right, 2x. All right, so values of x for which the series converges, we have to write that the absolute value of r, which is the absolute value of 2x, should be less than 1. Okay, so, or you can say that 2x must be between minus 1 and plus 1. In this case, it might be the easiest way to look at that. Okay, all right, so we can take it in 2. So 2x, taking the left hand side first, 2x is greater than minus 1, x is greater than minus 1 over 2. That's 1, all right, and then you can use this side, 2x less than 1, x is less than 1/2. Okay, so on the number line, okay, 0, 1, 2, they're negatives, 1, 2. The x values are to the right of minus 1/2. Now it can't be equal to it exactly, so if there's my half, minus 1/2, and to the left of plus 1/2, there's my possible values of x. So the maths itself over here is not particularly difficult, it's just inequalities. But you do have to know the theory of patterns and know what converging means, okay, to be able to answer that question. Okay, there's another recurring decimal question. Now I'm just going to start you off with this one. I want you to finish it yourselves, okay? So the recurring part there is 2, 1. So that would be equal to 5.21, 21, 21, and so on. Now clearly the 5 is not part of the pattern, so that what you do, you say break it up initially, say 5.0.21, 21, 21. Okay, now for this part, you break it up as we showed in the previous example, and you'll get s to infinity for that, and at the end you add back in the 5. Okay, so you can try that yourselves and see how you go. Okay, and that's just our syllabus there.